Hello everyone, welcome to CSCN 503, Introduction to Communication Networks. This is Dr. Amr Al-Mogi. It's my pleasure to introduce you to this course. I find communication networks to be quite an interesting topic. It's my field of specialization, and I always have a lot of fun teaching this course every year. You get to learn a lot of interesting concepts about the internet. You get to learn or to get a very broad overview about how the internet works. And by learning about the internet, you really get an idea about how any network works. And so this is roughly, let's say, the objective of this course, to learn about networking, to learn about the components of communication networks, to learn the architecture and the structure of the internet, and then to learn what we call protocols, which are basically the governing software or firmware of the internet, and learn basically how devices are able to communicate with each other. You learn different protocols that enable devices to perform different tasks in communication networks and thereby enabling people to communicate with each other from across the globe. Um, our teaching team consists of myself as well as two TAs. They are Ahmed Hilmi and Hana Medhat. Their contacts are available in this slide. We are all available for you at any time. If you have any questions or concerns, if you need to discuss anything, you can book an appointment or you can visit us in our offices. Okay. Yeah, this is roughly the course outline. When we discuss communication networks, we discuss the concept of what we call a protocol stack. And this is something that we will explain in details later in the course. And the protocol stack consists of layers. Each layer contains a set of protocols. And this is what we will be discussing in this course. Each protocol layer is responsible for a certain functionality in the network. For example, the application layer is where our applications reside. And so we'll be discussing these different layers, and with these discussions, we will understand how networks work. There is a textbook that you can use. It's called Computer Networking, a Top-Down Approach Featuring the Internet. It's a very comprehensive textbook, but all communication networks textbooks come with a certain feature. I'm not going to say disadvantage, but they are very wordy. They contain extensive discussions. Some people don't like that, but in any case, the book is comprehensive. All the discussions in the course are going to be following this book. What we do in terms of assessment in this course is shown in this slide. We have a final exam that is worth 40%, and the final exam is a comprehensive one. And so basically, all the content that is covered in this course will be covered actually in the final exam. There's also a midterm exam that is worth 20%. And the midterm exam this semester is going to be after the 7th week, not after the 6th week. Okay, so the midterm exam is going to cover roughly up to week 5, the content of week 5 or tutorial 5 in this case. Okay. There's also a project that is worth 20%, and it's a collaborative project. You work in small teams. And the project, I hope it's going to be an interesting one. You're going to be building your first website. You're going to get introduced to some of software engineering tools like HTML and JavaScript. And with those basic tools, you're going to build a website that has just some basic functionality. We're not looking for anything fancy here. We're just introducing you to the concept of developing a website and being able to communicate using a client-server model, a client being your device, and the server is where the website is located or implemented. And you learn how to actually establish a website that you can contact from anywhere in the world. It's also a good introduction to the software engineering course in the 6th semester, because some of these tools you will definitely need to develop the software engineering project. The final component of our assessment is the quizzes. They're worth 20%. There's going to be 3 quizzes throughout the course, and we're going to take best 2 out of 3 as we usually do. One note about teaching this semester. Teaching this semester is going to be hybrid, particularly in the tutorials. So in the tutorials, their number is going to be restricted to either 12 or 13 students, and you are required to attend in your own slot. Okay. So you cross attendance between slots are not going to be allowed. So each group is going to have 1 week face-to-face tutorials and 1 week online tutorials. Okay. The online tutorials have no attendance, but you are responsible for watching the videos yourself. Okay. All the content of the course is going to be recorded in videos and uploaded to the video on demand platform. Okay. One very important note is that the slides are not comprehensive notes. So you cannot just study from the slides. The slides plus what I say in the lectures, that's actually the content of the course, plus of course the practice assignments in the tutorials. But the slides are only meant to be remarks and pointers that I use to teach you. So they are not comprehensive lecture notes by any means. You can also use the textbook if you like. Or you can take notes, or obviously you have the recording, so you can refer to them at any time. Okay, now that we have the overview of the course, let's dive in to our first lecture. Our goal is to learn about communication networks, to learn how they work, to learn how devices communicate with each other. And so to learn about communication networks, we will take the quintessential communication network, which is the internet, the global network that covers the whole world, where all the applications reside, the one that we use the most. And so the internet is going to be our running example throughout the course. And so the first question that we can ask ourselves is, how do we begin to understand such a complicated structure as the internet? This is what we should expect, that the internet is such a complicated network. It's a global network. It has so many details. And so how do we begin to discuss such a complicated network? Whenever we have a complicated system, it's a good idea to always start with an abstraction, to look at something from a high level, to look at something from above, to abstract or remove the details as much as possible so that you end up with something that is simple enough to serve as a starting point. And with the internet, we can actually divide the internet into two parts. One part is called the core, and the other part is called the edge. The edge is where our devices reside. This is where our client devices, our what we call edge devices, this is where they reside. Now, when one of the edge devices wishes to communicate with another edge device, it has to inject the data into the core. And the core consists of high-speed switching devices. They come in basically two different forms, either a switch or a router. Switches are more used to connect smaller networks, local networks. Routers are the ones that are used to transport data across the internet. Okay, so you inject your data, what we call packets. So you inject packets of data, okay, into the core, and the routers are responsible for transporting these data packets from one router to the other until they reach a router that is connected to the destination or the end device that you want to send the data to. This is basically the high-level abstracted structure. You can expect that, of course, the internet is much more complicated than that, but in the essence, this is what we are actually talking about. We have an edge, we have a core. The edge is where most of the complexity of the internet is. This is where we find all the applications. This is where we find all the algorithms that serve our own needs. This is where we interact with the internet. The job of the edge is to just generate the data packets. You want to send them from one place to the other. You inject them into the core. The core consists of high-speed switches and routers. They transport the data packets until they reach the destination. Okay. This view of the internet is actually called the nuts and bolts view. It's a view of the hardware and software that makes up the internet. So basically, we have the edge, which consists of end systems. The end systems are the hosts, or the devices that we use, and they can also be servers. The servers are the ones that actually have the data that we're trying to access. So when you're trying to download a website, for example, from the internet, you contact a server, you send an HTTP request. This is something that we will discuss later. You send the request to the server, and the server already has the content. It just sends you the content back. And so the end systems, our devices, as well as the servers, are actually the edge. And then we have the switching devices or the routers that are capable of sending the data from one place to the other. And all these devices are connected with each other using communication links. And communication links come in so many different shapes and forms. They can be wired or wireless. Wired links also have different types. There are fiber optic links, there are copper links, which are the older ones. And there are wireless links as well, such as satellite links, mobile links, Wi-Fi links. These are all wireless links. And communication links are characterized by several metrics, the most important of which is the transmission rate or the bandwidth, which basically tells us how fast we can transport data through this communication links, how many bits per second. This is how we measure the transmission rate or bandwidth. Okay. Historically, there used to be only computers connected to the edge of the internet. So the edge devices consisted only of computers. Now this view has evolved. We have so many different types of appliances connected to the internet. You can have, for example, a smart toaster that prints the weather over your toast. So it's definitely connected to the internet because it needs to actually have the weather forecast. You have picture frames, you have IoT, Internet of Things devices, you have internet phones, you have so many different types of edge devices that are now connected to the internet, not just computers. So when we say the edge, we have to actually think of many, many more devices, not just computers and servers. Okay. So the other part of the nuts and bolts view is actually the software or the firmware that is actually running the internet. So we said that the nuts and bolts view consists of the hardware and software. The hardware is basically the routers as well as the edge devices and communication links. The software part, or more accurately, the firmware part, is the protocols. If you ask yourself, how can two devices, the devices that are not essentially smart, they just understand electricity, they understand binary, how can they actually understand each other? How can they communicate with each other? They can communicate with each other just in the same way as two people can communicate with each other. If you have, for example, a situation like that, you walk up to someone and you want to ask them about the time. The only way that you would get a response is that if you and that other person are actually speaking the same language. And there is a way that you approach someone to ask for the time. You don't just jump into someone's face and say, "What's the time?" You go and say, for example, "Hi," or "Hello," or "Good morning," or whatever. If you get a response, then you proceed with your question, which is, "Do you have the time?" And they give you the response, which is, for example, 2 o'clock, or they tell you, "No, I don't have a watch," or whatever. If you say hi to someone and they don't respond, that means either they don't understand your question or they do not wish to answer. In both cases, you do not actually proceed with your question. Okay. The indication that you can actually proceed with your question is that if you actually get a response, that's when you can ask for the time. This is a protocol, and it's an implicit protocol that we have between humans. We do it without actually recognizing that it's a protocol. And we do that in so many different scenarios of our lives. Communication networks need a similar structure to be able to understand each other. When a client wishes to communicate with a server to download a web page, it needs to communicate with that server using a fixed structure, especially because they are machines and they will not understand actually diversity in communication. They must have a very rigid structure. So for example, if a client wishes to communicate with a server, if the type of communication is what we call a TCP communication or something that uses the transmission control protocol, again, it's just a type of protocol that we will discuss later in the course. Instead of saying hi, the client will start by sending what we call a connection request. It's a request to the server saying, "I wish to actually communicate with you." If the server responds, that means that, first of all, it understood the question, it understood the request, and second, that it is willing to respond. That means it has, for example, sufficient resources to respond, or it has time, or it authenticates the client, or it has services that it can offer to the client. Whatever it is, the server is actually now willing to respond. Once the server responds back to the client takes this as an indication that now I can actually send my HTTP request. I can ask for the resources that I want, and then the server sends them to me. This is actually what a protocol is. It consists of the format, order of messages sent and received among network entities and actions taken on message transmission and receipt. This is actually what a network protocol is. It defines the format of the messages, meaning what does a message look like from the inside. If you open a TCP connection request, or if you open up an HTTP request, what's inside? What's its format? It needs to have a fixed format. It's not just anyone can actually write anything. Otherwise, the machines will not actually understand each other. So what is the format? What is the structure? What comes before what in a specific message? So the format is defined by the protocol, and the order of messages is also defined by the protocol. So in the TCP protocol, it is understood that you must send the TCP connection request, you receive a connection response, and then you send your HTTP message. This is a fixed order. It cannot be changed. If it is changed, the devices will not actually understand what you're trying to do. So this is also defined by the protocol. And the final thing that is defined by the protocol are the actions. Once you receive a message, what do you do? Once you receive a TCP connection request, what do you do? For example, servers will open what we call a socket, something that we'll discuss later in the course. It will open a socket and get ready to receive the HTTP request from the client. This is an action that the server will take upon receiving a connection request. So whatever the action is, it is also defined by the protocol. And so parts of the nuts and bolts view of the internet is the set of protocols that is governing how devices communicate. There are different protocols because communication networks are very complicated, especially something like the internet. You have so many different functionalities. You have, for example, routing, how to discover a path from source to destination. You have establishing a connection between source and destination. You have security protocols or security features. You have the data itself, the application layer data, I mean. How is it actually sent? You have so many different functionalities and services that need to be offered in a network. So you need a set of protocols. You need actually a large number of protocols. Examples are included in the slide, such as the TCP protocol, the IP protocol, which is where your IP addresses come from, the HTTP protocol. Skype has a set of proprietary protocol because it's owned by a company. It's not public protocols. There is the Ethernet protocol, which we will discuss actually, I think, in this lecture as well. So there are several protocols, each one doing a particular functionality in the network. And together, all these functionalities serve to make the machines understand each other and be able to deliver data to each other. These protocols are not just out there, they are organized into layers, which we call the protocol stack. And this is going to be the focus of the course, something that we will discuss in the next lecture. Okay, so now the question is, where do these protocols come from? Who proposes them? There is actually only one institution that is responsible for standardizing protocols into internet, and it's called the Internet Engineering Task Force. So each protocol gets what is called an RFC number. RFC is short for request for comments. So for example, TCP has an RFC number. IP version 4 has an RFC number. IP version 6 has a different RFC number. Each protocol in the internet, HTTP, all these protocols, they actually have a certain RFC number. It's just a number for the standard. Now, does this mean that you cannot actually propose a protocol to operate on the internet without the permission of the Internet Engineering Task Force? That's actually the nice thing about the internet. It's not owned by anyone. It's actually just the largest global distributed network. So if you don't like, for example, how the IP protocol works, you can propose a new one. Your only challenge would be that you'd have to convince 7 billion people around the globe that they should use your protocol instead of actually the IP protocol. So because the internet is a global network, it's difficult to actually propose a new protocol. I'll just give you an example. IP version 6 was introduced in the early 2000s, and up to this date, it is still not actually the main version of the IP protocol that is used. Still, IP version 4 is used. So that's over 20 years that it's taking to convince everyone around the world to ditch IP version 4 and use IP version 6. It is difficult, which is why once the Internet Engineering Task Force gives you the stamp of their approval, gives you an RFC number, this is an indication that your protocol is a good protocol. It's standardized enough that people should actually start adopting it or accepting it if they need. Okay, so this is basically the nuts and bolts view of the internet. It's a view that consists of the hardware and the protocols that are in the internet, so that we see actually how all these fit into each other so that you can actually send and receive data. There is another alternative view of the internet, which is what we call a service view. Basically, if you think about the internet as a global communication network, what do you want from it? What do you expect from it? These are actually the services that are offered. For example, when you make a voice over IP call, when you make a call, for example, over Zoom or something like that, what services do you expect from the internet? What do you want the internet as a network to do for you? Most probably, you'll want the internet to deliver your packets very quickly. You do not want delay. You do not want the video, for example, to freeze. These are all services that can actually be translated into networking metrics that the network should actually deliver to you. This is the service. When you send an email, on the other hand, what kind of services do you want the internet to offer to you? Most likely, you never actually send an email and it is received with errors. It might not be received at all. So that's a failure in delivery. But once it's actually delivered at the destination, it never actually has errors. You don't send a word and it's delivered as another word. This is because the internet offers you a service which is called reliable data delivery. It guarantees that when a packet is delivered to the destination, it is not going to be accepted unless it is without errors. So it gives you a way to check for errors. It doesn't guarantee that all the packets will be delivered because certainly your email can be lost. But if it is delivered, it is going to be delivered without errors. There are different kind of services that applications quite often require from the internet. It is actually important to mention that the internet at its core is a best effort network. It means that the internet can never actually provide you any guarantees on any network service. For example, if you have a Zoom call, we have all experienced times where the connection quality is bad. You cannot actually see the person that you're talking to. The voice is slow or it's lagging, or there are silent periods or anything like that. That's because the internet is only a best effort network. And best effort doesn't mean that it's going to give you a bad service. Best effort actually means that it's going to give you the best service it can afford. So the internet, because it can be accessed by anyone around the world, you can never actually predict when people will use its resources. So at any given time, there may be an abundance of resources or there may be limited resources. The internet tells you, I'm going to give you the best resources that I can at any given time, but I cannot guarantee for you that at a specific time, I'm going to have some available resources for you, meaning there is no resource reservation. It's a best effort network. Okay. Now that we understand roughly the two types of views of the internet, we can now dive a little bit deeper and look into the two parts of the internet that we have discussed. So we have our core, the routers or the switching devices, and we have our edge, which consists of the client systems that we have. So we want to start by looking a little bit deeper into the edge. Okay, so what do we have in this edge? We have applications and hosts. We have what we call access networks. So you might ask yourself, once your edge device actually generates a packet and it wants to inject it to the core, okay, how does it do that? How does it inject a packet to the core? It does that through something called an access network. The access network is basically a bridge, something that connects your edge device to the core. Okay. There are many types of access networks and we use them all the time. For example, we have DSL, we have our mobile network, which is essentially a type of access network, even if your mobile network covers the entire country of Egypt. It doesn't matter. Still, its job at the end of the day is that it takes your packets from your phone and injects them through the internet or through the internet core. So it's a very big access network, but it's still an access network. For example, your Wi-Fi network at home is a type of access network. It takes the packets from your phone or from your laptop and again injects them through the core. So whenever you want to send packets to the core or receive packets from the core, you need an access network. Your destination, which is basically where you are sending the packets to, also needs an access network to be able to receive packets. Okay? So whenever there is communication between two devices over the internet, mainly two types of communication models between clients over the internet, which is either the client-server model or the peer-to-peer model. The client-server model is the more prevalent one. This is the one that we find the most. And here, the clients do not talk directly to each other. If one client wishes to communicate with another client, it has first to send it to the server, and then the server will send it to the client. That means all the communication is between the client and the server. And typically, the client is the one that initiates a communication session, and the server is always on. It's always waiting for the requests. Okay. We call the client server model actually infrastructure intensive. That means you have to invest a lot of money to create the infrastructure, to implement servers, to have a database, to have a data center, so that you have enough servers that are on all the time, such that they are actually always ready to receive the requests of the client. Okay. The peer-to-peer model, on the other hand, clients can actually communicate with each other directly. So if you have something that you want to send to a destination, you actually just send it right away. So how would you know that your application is either a client-server application or a peer-to-peer application? Most applications are actually client-server. So whenever you're actually downloading a web page from a website, this is definitely the client-server model, because you have a server, you're sending it a request to receive content, and the content is sent to you from the server. Some applications are peer-to-peer. Torrents is usually the perfect example for that. In torrents, many people around the world have chunks of a file, and when you want to download this file, you download the chunks. You actually access the devices of all these peers, and you get the chunks from them. They upload the chunks to you directly, and this is why it's called the peer-to-peer model. There is definitely going to be a BitTorrent server, and this is only where the IP addresses of the peers are saved. So how would you know which peer that you should access to actually receive this content? You go to this directory or the BitTorrent server, you get the IP addresses, and then you download the content directly from them. Okay. Some applications are a little bit confusing. We are not sure whether they are client server or peer-to-peer. For example, something like WhatsApp or any chatting application, Facebook Messenger, for example. Is it client server or is it peer-to-peer? You can infer that if you look at the functionality of these applications. For example, with WhatsApp, if you send a message to someone and that person is not online, their phone battery died, for example. Once they charge their phone and they switch it on, they will actually receive those messages. So if they receive the messages once they open their phone or they switch on their phone, where were the messages saved? They were not at the originating client. They were not at the source, because the source already sent them. So where were the messages saved? The answer is that they must have been saved at a server. So WhatsApp is actually a client-server model. When you want to send a message to someone, you don't send it directly to that person. You send it to a WhatsApp server, and the WhatsApp server forwards it to the destination. Even if it's a group message, you send it to the WhatsApp server, and the WhatsApp server fans it out. It creates multiple copies and sends it to all the members of the group. Facebook messages are the same. What if you have video calls over Facebook Messenger, for example, or over Skype? Is this a client server or is it peer-to-peer? We can actually say it's a little bit of both. It's hybrid. Because with the Skype application, for example, you have to first contact the Skype server to get the IP address of the recipient. So when you want to establish a call with someone, that someone has to actually be online. You can't have a video call with someone who is offline. So once someone becomes online, they register their identity and their IP address at the Skype server. And now it becomes available when you want to talk to this person. If they are in your list of contacts, you get their IP address from the server. And once you get the IP address, you can establish the connection directly between them. That means the connection is actually peer-to-peer, but obtaining the IP address is client-server. Okay, now back to our discussion about access networks. So you need an access network to be able to inject your packets into the core or get packets from outside of the core. And we said that there are many types of access networks, and there has been actually many types throughout time. Okay. Historically speaking, the access network that we used to use up until maybe early 2000s is something that is called dial-up internet or dial-up model. Dial-up internet is actually just a type of access network. And the idea behind dial-up internet is that it uses an infrastructure that is already widely available, which is the telephone infrastructure, just the landlines. So people, when they invented dial-up, they thought, "Oh, we already have an existing telephone network that covers the entire country. Why not just actually allow people to use it to transfer data instead of actually transferring only voice?" And therein lies the idea. When you want to establish an internet connection using dial-up, what you do is you make a phone call between your home PC and a server in the internet. It's actually literally a phone call. That's why you are actually given phone numbers. If you remember dial-up, or if you are old enough to actually have used it once in your life, for example, you would have to make a phone call. There was a phone number you inserted in your PC, and you make a phone call to your ISP, your internet service provider. Okay. Now, because the telephone network is inherently an analog network, while your home PC is obviously a digital device, you need something to convert between analog signals and digital signals. And this is called the modem. And it's short for modulator, demodulator. It converts the digital signals from your PC to analog so that they are injected into the telephone network. And once they reach the internet service provider, there is another modem that converts the analog signals back to digital so they can be injected in the internet. So your request goes in the internet. Once the response comes back, it comes to the ISP. The modem converts it to analog. It travels over the telephone network. It reaches the modem at your house, and it gets converted back to digital, and then your PC can understand. So there again is a phone call between your modem at your home and the modem at the ISP. Okay. Now, because the telephone, the voice calls over the telephone network, or they support only voice, the bandwidth of voice is usually between 0 and 4 kilohertz. And so the bandwidth of telephone networks for telephone calls is usually just very small. And this is why dial-up internet could only achieve data rates up to 56 kilobits per second. And you could only use either the phone or you'll be on the internet. So that was actually something very annoying. If you're on the internet, you're trying to download something, and someone in another room picks up the phone and tries to make a call, your internet connection gets interrupted. So because that was incredibly annoying, the next upgrade for access networks was something called the digital subscriber line. And here it's actually roughly the same idea. We're still actually using the telephone infrastructure. Okay. Except that now we don't restrict ourselves with the 0 to 4 kilohertz bandwidth of the telephone network. This is actually not the bandwidth of the telephone infrastructure itself. It's just the bandwidth of a voice call. But the infrastructure itself is made of copper wires. Or historically, it used to be made of copper wires. Now everything has been replaced with fiber optic lines, which is much higher in bandwidth. But even for the copper wires have actually a much larger bandwidth, larger than 4 kilohertz. The bandwidth can actually go up to 1 megahertz. And so the idea in digital subscriber lines is that you use the entire bandwidth of the telephone network and not restricting yourself to making a phone call with a bandwidth of 4 kilohertz. Now, how do we open up the bandwidth of the internet, of the telephone network? How do we not restrict ourselves to the bandwidth of a phone call? This is where that small device that you have at home that many people might not actually know what it is for, which is called a splitter. The splitter is basically a filter. It takes the frequencies belonging to a voice call and sends them to the phone, and it takes all the higher frequencies and sends them to the DSL modem. You still need the modem because you're still using the telephone network, which is analog, still analog, but the signals generated by your PC are digital. Here now, it is a different type of modem. It's a DSL modem. So you take the frequencies coming from the splitter that are for the internet, and you send them to the modem. There is another digital subscriber line access multiplexer, which is basically just another type of splitter. And it takes the frequencies that are in the voice range and sends them through the telephone network if it's a voice call, and it takes all the other frequencies and injects them to the internet. So the DSLAM is a splitter for the ISP slash modem as well. Okay. And now, because you are using the splitter, you are able to make a phone call and be on the internet at the same time. You don't actually have to pick and choose. So this was a definite upgrade, and digital subscriber lines are the ones that we have actually at home right now. The back end or the backhaul infrastructure of the country has been largely upgraded from copper wires to fiber optic cables, not to the home. So what happens is that you have fiber optic cables between the telephone box that is close to your house and the central office, central basically. This is very important because it means that it is no longer important how far you are from the central office. It used to actually be the case. When you go to your internet service provider and subscribe for a certain data rate, for example, you say, I want a very fast internet connection. They will tell you, well, where do you live? Because if you live very far away from the central office, they will not actually be able to offer you a very high rate because the signal weakens with distance over the copper wires. Okay, so if you live very far away, you will only actually be restricted to smaller data rates. This is no longer the case with fiber optics. Fiber optics, they have a much longer range, and so even if you live far away from the central office, they will still actually be able to offer you any rate you want. And again, the fiber optics connection is between the central office and what is called the telephone box that is close to you. And then you actually have a copper cable coming from the telephone box to your house. But this distance is very small that it is no longer relevant. In North America, the US and Canada, they have a different type of access network, which is called cable modems. They used a similar idea, but for a different type of network. Basically, they noticed that many people are using cable television. Okay, this was actually the prevalent TV network in North America. So many people were using already cable TV. And so they had the similar idea. Rather than actually using the telephone network, let's actually just use the TV network. And the nice thing about this idea is that the TV network was already built with fiber optics cables. Again, the fiber optics cable connects the central office or the central stations to a box that is near your house, and then you have not a copper cable, but something called the coaxial cable to your house. The fiber optics cable and the coaxial cable have actually higher bandwidth than the copper wires that we have for the telephone network. So initially, cable internet was much faster than DSL. Now they are more or less similar. DSL has evolved enough such that they have similar speeds to cable internet. And this is roughly what the structure looks like. You have a cable head end. This is where the TV signals are generated, all the TV channels, and they are sent using a fiber optics cable to the houses. And so if you want to have internet on top of that, you implement some servers at the head end, and at the houses you have a structure that is similar to DSL. So you have a modem and you have a splitter. Now the splitter will send the TV frequencies to the TV and will send all the other frequencies to the cable modem to be converted from analog to digital, because the TV network is still analog, and then they're sent to the PC. It's a similar method, but with a different type of network. Okay. Another type of access network is called actually institutional access. This is what we have in organizations, for example, like the GUC. You want to connect a very large number of devices to the internet. You have, for example, all the offices where the TAs and professors, they have computers and they want to actually access the internet. Obviously, it is not feasible to provide each and every one of them with a separate internet connection. So what you do is that you have what we call an Ethernet internet access. You basically have a switch. For example, here at the GUC, every floor has a switch or maybe a set of switches depending on the number of offices, and you connect all the devices to the switch. So if the devices wishes to communicate with each other or communicate with an intranet server, intranet meaning that it's a local server inside the network, inside the GUC network, switch. So when we as faculty wish to access the internet, for example, to upload an assignment or to change a grade or to enter attendance or to do anything like that, we're accessing actually an intranet server, and the communication is typically forwarded using a switch. As we said, the switch is also a device that is responsible for forwarding packets. We will learn how later, but it is for smaller networks. Now, if someone wants to access the internet, there is an institutional router, which is called the default router. Okay, you send the package to the switch forwards them to the router, and then they are sent to the ISP or the internet service provider. Okay, once the response comes back, it comes to the institutional router, which sends them to your device through a switch. Okay, the standard or the type of protocol that the switches use is called Ethernet. If you know the twisted pair copper cable that is plugged into devices, this is actually an Ethernet cable. And Ethernet, it's an old standard, and it has many versions, and the versions have different speeds. Typically, you will have either the 100 megabits per second Ethernet for devices that are connected locally. Now, 1 gigabits per second is also have become quite prevalent. 10 gigabits per second or 100 gigabits per second are for backhaul links. That means you want to connect a switch with another switch, or you want to connect one building to another building, for example. Okay. The last type of access network that we will discuss is wireless access networks. These are very important because they support a very important functionality, which is mobility. You want to have an internet connection while you're on the go, while you're in your car, or while you're moving around. You don't want to be restricted to a wired connection. You use a wireless network. Typically, or actually now historically, wireless networks used to be slower. Now wireless networks are able to achieve actually very high speeds, especially wireless local area networks or wireless LAN, so typically Wi-Fi. Wi-Fi is also a standard. That means if your device is communicating with Wi-Fi, it is using a standard that is called 802.11, and it is produced by an institution that is called the IEEE, Institute of Electrical and Electronics Engineers. And this institution is responsible for standardizing communication protocols. And so this standard over the years have had several versions. The first one was 802.11b, and it achieved a data rate of 11 megabits per second. The one that came after that, and it was used for a long time, which was called G. G was able to achieve a data rate of 54 megabits per second. And then there was 802.11n, which achieved the data rate of, it could go up to 600 megabits per second, but practically it was 100 megabits per second. And the one that we have now mostly is 802.11 AC, which can communicate at rates up to 1 gigabits per second or faster. This is for wireless LANs. Wireless LANs, as you can see, are very fast, almost as fast as wired links. However, they have a limited mobility range. That means a Wi-Fi access point can cover up to maybe 100, 200 meters, not more than that. If you want to have wide range mobility, then we're actually just talking about cellular networks or mobile networks. The standards that we have right now are 3G plus or HSPA. LTE is, of course, the 4G standard. And up next, we have LTE Plus, which has already actually been implemented in Egypt. You might find your phone saying 4G Plus. And of course, we are waiting for the deployment of 5G anytime soon. Okay. At home, you have also an access network. We call it your Wi-Fi router, but it is actually more complicated than that. Wi-Fi router is a name that we give to a collection of devices that are within the same hardware device. So if you open up your Wi-Fi router, but I mean, don't do that unless you know how to put it back. Inside, there will be a DSL modem because it is a DSL connection. So the DSL modem is what connects you to the central office and connects you to the internet service provider. There is also a wireless access point that has actually the standard, the 802.11. Probably now it is 802.11 AC. Okay. This is the one that is providing you with the wireless connectivity. This is the one that is sending and receiving the wireless signals. But it does only that. It gets the data from the ISP, converts it to wireless signals, and sends it or broadcasts it through the Wi-Fi network. And then your device will pick it up because it's a wireless signal. It goes everywhere. Okay. There is also a router that connects the wireless access point to the DSL modem. Okay, and any Wi-Fi router in its back, you will also have ports where you can plug in a wired connection to your device. Okay. Collectively, all of this, we just call it the Wi-Fi router, but you can see that it's much more complicated than that. It has a Wi-Fi access point, has a DSL modem, and has a router built inside so that you are actually able to communicate with the internet. That's it for lecture one. Starting next lecture, we will take a look at the second part of the internet, which is the network core. Talk to you next time.